In this video, we're going to be discussing double and triple bonds. And just a reminder, double and triple bonds happen for covalent bonds only. So in other words, when you have two metals bonding together, they can form single bonds, and sometimes they can form double or triple bonds. Let's take a look at a variety of chemical formulas and see how they would actually bond together. So we'll start off with fluorine. Fluorine, if you look at the periodic table, is a halogen. So we know that fluorine has 7 valence electrons. And so again, it's very important that we carefully draw those dot diagrams. We want to use those dot diagrams to do all the work for us. All right, so here are my 7 valence electrons, and based on my dot diagram, I recognize that wherever there is a single electron, valence electron, that is a potential bonding site. So I've got a potential bonding site right over here. I don't have any bonding sites on the top, on the right, or on the bottom, because once you have 2 electrons in one region, that means that they are no longer going to bond with anything else. So potential bonding site. Now I have 2 fluorines, and when I look at 2 fluorines, each having their one potential bonding site, they can beautifully bond together. And I'll go ahead and start color coding my electrons so that it makes it a little clearer. There we go. And the key is that each of these atoms, except for hydrogen, always wants to have 8 valence electrons. So let's take a peek by creating circles around them to see if each of those has 8 valence electrons, and in fact they do. Remember, there's always going to be an overlap in the circle because they're sharing those electrons. If I were to draw a molecular structure for that, wherever I have 2 dots bonded with 2 different atoms, I create a dash, okay? Just a reminder that dash equals always 2 electrons. So I'm not going to forget my lone pairs. Those are going to be very important later on. So now let's try a different chemical. We have oxygen. Oxygen, we recognize here that there are 2 oxygens. Remember that we always need to create a molecular structure or a Lewis dot diagram in which all of the elements have 8 valence electrons. So let me go ahead and draw the dot diagram for oxygen. Oxygen, if you look at the periodic table, has 6 valence electrons. Right, this now presents a problem. You're going to be recognizing that we have a bonding site here, a bonding site over there for both oxygens. But there's only one other atom that needs to bond together. And in the case of if we were to create this diagram, where these 2 oxygens bond together, we still have a single electron here on the bottom for each of those oxygen. And if I draw a circle around there, this oxygen has not gained 8 electrons, or it does not have 8 electrons, it only has 7, and that's not good enough. Remember, the octet rule or the noble gas configuration always says we need to have 8. And so the way that these atoms adjust for that is that they decide to then share yet another set of electrons. So this electron and this electron are going to come together at the place where those 2 oxygens are bonding. And if I were to redraw this, we now have this configuration. Just a reminder, these right here, these 2 electrons are originally the ones that were these bottom ones. They've just moved to the place where those 2 oxygens are bonding. Let's take a look whether or not that fulfills the octet rule. Well, it just so happens this has 8 valence electrons and this one has 8 valence electrons. All right, so whenever you have a situation where you think you might not have enough atoms so that it can fulfill the octet rule, instantly start thinking, let's share another set of electrons and create, in this case, what we call a double bond. Just as a reminder, every 2 dots equals 1 dash. So theoretically, I could now draw a line between these two and a line between these two. And so oxygen right now is going to create a double bond. Now, don't forget those lone pairs. And because electrons repel each other, remember electrons are negative charges. They don't want to get close to each other because a negative repels a negative. I'm going to now draw these lone pairs as far away from each other as possible. And kind of consider that like you were going to take a pie and you want to divide it into 3 pieces. There we go. So the oxygen would be here, or 3 equal pieces, and those lone pairs are there. That's the furthest away it is. I know that sounds a little bit odd, but that's how I tend to remember it. Okay, so let's just double check. Does this oxygen have those 8 valence electrons? Yes, it does. Does this oxygen? Yes, it does. All right. So those are what we call double bonds, okay? And the time I start thinking about double bonds is when I'm recognizing I do not have enough atoms so that the octet rule or the full valence shell can happen. Let's take another example. Here we have nitrogen, and I have 2 nitrogens. So again, let me draw the dot diagram for nitrogen. I look on the periodic table, and these 2 nitrogens have 5 valence electrons. All right, so we have for each nitrogen now not 1 bonding site, but 3 bonding sites. There's one on the left, one on the right, and one on the bottom. We can already predict that we're going to have some types of situation here. So let's go ahead and start bonding it normally with each other. Okay, so they share their electron right over here. Okay, and then I have a single one here and a single one there. So here we're presented with exactly the same situation, in which case I only can use two nitrogens because it tells me I can only use 2 nitrogens. But if I were to draw a circle around this nitrogen does not have 8 valence electrons. It only has 6, and that's the case for the other nitrogen as well. And it needs to have 8. So now I start considering if I were to have these nitrogens share yet even more electrons, would that work? And so what I'm going to do is I'm going to move this one down here and this one down here. I'm going to move that one over here and this one over here. And you'll notice that by doing that, I now have in between these 2 nitrogen atoms a total of 6 electrons. And then these lone pairs, I'm going to move them as far away from each other as possible, so that would put them on these ends. And now I have something that we call a triple bond. And triple bonds are not that common in the real world because it takes a lot of energy to form these triple bonds. Most commonly are single bonds and double bonds. Let's again just double check. Do we have those 8 valence electrons? We certainly do for each of them. Okay. All right. Let's try the last one. We have silicon dioxide. We'll be discussing how to actually name these chemicals in our class after this. So for silicon dioxide, I always start with the least electronegative, so I'll start with silicon. Silicon has 4 valence electrons. Oxygen has 6. All right, and remember, we're always building on the least electronegative chemical, so that's silicon. And what I'm going to do is I'm going to build on opposite sides of it. So rather than add silicon, oxygen, and an oxygen, I'm actually going to put one oxygen on one side, and that's something I always want you to do. Consider this silicon, the least electronegative, what we call our central atom. And for that reason, you want to surround your other atoms with that silicon. All right, so here we're presented with a problem yet again. We have a bonding site right over here. We have a bonding site right over here. We have a bonding site right over here, and we have one right over here. However, remember, I only have one silicon and 2 oxygens. So I instantly need to start deciding, would it make sense for these to start sharing electrons? And I can certainly have this one move here and that one move there. I can have this one move there and this one move there. And let's see whether or not that does the trick. So now I have oxygen having a double bond, silicon having a double bond, and then don't forget my lone pairs. These are going to be really important. Again, I'm kind of distributing them so they're as far away as possible. Let's see whether or not this fulfills our octet rule. Thanks to this double bond, this oxygen is good to go. With these 2 double bonds, silicon is good to go. And with this double bond, oxygen is also good. And remember, good to go means that it has 8 valence electrons. So let's draw the molecular structure for that. I always like to start with my central atom. I have 2 bonds. I show that by 2 dashes. I have oxygen that has those 2 lone pairs. I try to keep those electrons as far away as possible.